So, we will do an application, okay, where we will employ the perturbation technique, or rather perturbation methods that we will use to compute some quantities of phase transition. Okay. So, I need to explain exactly what we are after, and phase transition by itself is a very interesting topic. Okay. So, I am going to cover very important aspect of phase transition, okay, which won several Nobel prizes. Okay. So, I will tell you what is the question we are after. So, phase transition everybody knows, no? I mean liquid to vapor, solid to liquid, ferromagnet to ferromagnet. So, we see all solid, liquid, vapor transitions, and so this is called phase transition, phases, 3 phases and their transition. We will stick only to that. So, there are many examples. I said para to ferro, water to vapor, solid to liquid. Now, you might have heard this word first order and second order. So, first order, so there is a free energy F, right. So, free energy, if I take the derivative with related to temperature, then I get entropy. Okay. I may have missed the sign, but this is entropy. Entropy is the first derivative of free energy. So, if entropy is discontinuous, okay, then we say it is first order. So, you will find that for solid to liquid, okay, their density is different, no, solid to liquid density is different. So, that is a first order transition, but there are situations where the entropy is not different for these two phases. Okay, we need, well, for first order transition we need a latent heat to compensate this change in entropy, but it turns out sometimes we do not have discontinuity in the entropy or density. So, this is a special situation. So, I do not want to get too much into this. So, the phase diagram, well, so basically temperature and pressure, not temperature. So, it goes like this, no, liquid to vapor. So, I am not thinking of solid, okay, this is this. So, this line. So, liquid to vapor, I need certain latent heat for typical temperatures, like for water we need at 100 degrees, we will need some latent heat, but you keep pushing the pressure in such a way that the temperature, transition temperature is beyond 100, and at some critical temperature you keep pushing, okay, keep pushing the critical temperature higher and higher at some pressure. So, I am increasing pressure, at some pressure and temperature there is no change in the density. I am not sure whether you heard about this or not before. Okay. So, here if I go from liquid to vapor, so this vapor phase and the liquid phase, I go like that, there is no change in density, but here there is a change in density, okay, and this point is called critical point, and here since density is not changing or entropy is not changing, this is second order transition. Okay. This is important difference. It turns out that, so this is for liquid vapor, and we are going to focus on this fixed point. That is where several Nobel prizes went to. Okay. So, the ferromagnet to paramagnet or para to ferro. So, if you decrease temperature, so beyond critical temperature there is only para, mean magnetization is 0, no, there is critical temperature, mean magnetization, but below critical temperature we get the magnetization curves looks like this. Okay. Here magnetization starts from 0, there is no change in magnetization, well, at the critical point it starts to increase slowly if I decrease temperature. So, this is also second order transition. So, para to ferro is second order transition. Now, I will not do this in detail how the entropy is and so on, but this is called second order transition, because here the change in magnetization is increasing slowly from 0 to non-zero values. The way it happens here, density is 0 here, but if you go to lower temperature then the density difference will increase slowly here. I hope this point is clear. At this point, you can see my cursor. If I decrease my temperature, my density difference varies slowly. In fact, there is a formula given by Landau that magnetization is T minus T c to the power half. Okay. If I decrease more, than my magnetization will be more. Okay, that is we will derive this formula. Okay, this half. It turns out in experiment the exponent was not found to be half, it was different than half, and that is where the problem was. People did not know exactly why it is not half. Okay. So, I will so that correction to half is what we will discuss today, but today and not today, but including today plus some more lectures, so it is a difficult theory. Okay. So, now this is for phases, but we can apply this to other systems as well, for example, mob behavior. Okay. So, mob is not individual. Okay. So, individual may act very differently and mob acts very differently. So, it turns out this is a mob is not collection of individuals. Mob is a collection of individuals, the mob has its own behavior, and we will find some of it happening in phase transition, during the phase transition. Okay. So, presently we are not going to discuss this is more complicated, but we will discuss second order with a generic free energy. We will assume equilibrium behavior. So, time dependence will be 0, there is no time dependence. So, it is in a heat bath because I have temperature heat bath, and I look at the behavior of the system. And so, we are looking at physics during phase transition, physics around phase transition. We will focus on this region, and I am going to take magnetic system as an example, not liquid vapor system. It is slightly more complicated, but this one to one mapping, it turns out these two systems behave exactly the same, exactly, not approximately, exactly the same near the phase transition, but that requires mapping. We will focus on magnetic phase transition, magnetic transition, okay, to para to ferro. That is what will be my discussion on. So, one of the leading theory of phase transition, PT is short form for phase transition by Landau. Okay, this is a picture of Landau. So, what is the theory of Landau theory, which you might have done in your statistical physics course? So, we start with free energy. Okay. Free energy is like Hamiltonian, but it is in a heat bath. So, free energy is slightly more technical, but for this course we will not get into the technical aspects. So, free energy, so this phi is, you can think of magnetization. Okay. So, this is a local magnetization. So, we have a lot of spins, some imagine is Ising spin up down like this. So, these three together gives you non-zero magnetization, right, when down. These two gives you positive magnetization. In ferromagnetic state it is totally 0, but there are fluctuations, no, some place it is small positive negative, some place it will be more positive, so more negative. Paramagnetic it is 0, but ferromagnetic has non-zero value. Okay. So, this phi is the magnetization. And phi is function of both a position and time, but we are going to suppress time. Of course, function of time, but I am going to look at equilibrium behavior. So, time is basically silent, I do averages. Okay. So, what is the free energy look like? So, this is postulated by Landau. Landau proposes that there is a constant part, and there is a part which is phi squared quadratic. Remember, we had m square phi square plus grad phi squared plus phi 4. So, you can see all the terms are appearing here, and this is a connection of statistical physics with particle physics and other fields. This is one of the famous theory called phi 4 theory. Okay. Please remember this phi 4 theory, because other than the linear part we have phi 4 term. okay, and there is a reason why phi 4 is a leading order term, I will tell you in a minute. Okay. So, first term is R naught phi squared, R naught is lambda postulates is proportional to T minus T c. T is the temperature and T c is the critical temperature, and the coefficient in front, but I will not keep, there are too many coefficients already, R 0, C 0, U 0, H. H is a magnetic field. Okay. Now, the second term is coming from the fluctuations. So, there is a gradient of fluctuation which also matters, C naught grad phi squared, okay, is a very important term, it is a potential energy current time kind of term. Now, this is the interaction. Now, I did not tell you the derivation, but the coupling between spins is captured by this U4 U naught phi 4 term. Okay. So, this is a important term which is responsible for phase transition, without that we will not have phase transition. Okay, is going to come in a minute. So, phi 4 is plays a critical role for phase transition, and H phi is the interaction sigma dot B, you know. So, H phi is a interaction of magnetic radiation with the external field, and H will also act like a source term. Okay, so if you need something, but yeah, H is the source term if you like. H is a magnetic field, external magnetic field. Okay. Now, why do not we have phi cube term? The reason why Landau says no phi cube term, because the magnetic system, magnetic energy is same for magnetic up and magnetic down. There is a symmetry, up down symmetry in the for Ising spins. Because why should a up spin system with up spin have more energy than the system with down spin? So, that is why all odd order terms are not included, because phi cube will change sign. So, it will decrease for minus and increase for plus. Okay. So, these are ruled out because the system has up down symmetry. Okay. So, rotation symmetry says the system must be of certain form, and that is what is happening here. So, we keep only the leading order term is phi 4. There could be term like phi 6, and we do not keep phi 6 for second order transition. First order transition requires phi 6 term. Okay. But I think we will not get into it, because that discussion itself is a reasonably complicated term. I just want to, if you are interested, you can look at it. If you put phi 6 term, then you get hysteresis and first order transition. Okay. But we are doing second order, for which phi 4 is sufficient. Okay. So, Landau theory, how does it proceed? So, this thing. So, please remember that R naught is like m square term, what we discussed before, is the mass term, okay, mass squared. Effective action is the integral, no, ignore right now this lambda, do not worry about it, it is an integral of the whole system. So, this is the volume integral, okay. And so, we will do mean field theory. So, Landau does mean field theory, I will do more than mean field theory later, but Landau assumes mean field, that means grad phi is 0. So, it is a constant field everywhere, okay, grad phi, there is no variation of phi. Okay. So, this is my potential. Okay, phase transition says H is 0. So, when you have ferromagnet, it is in the absence of magnetic field. When you put in magnetic field, of course, there is a net magnetization, but we are looking at magnetization in the absence of magnetic field. Is it non-zero or 0? So, we are looking for average M. Is it 0 or non-zero when H is 0? If it is 0, then it is paramagnet. If it is not 0, then it is ferromagnet. Okay. So, let us plot the free energy. Okay. So, when I plot it, so my parameter is I change the temperature, U naught you are not changing, U naught is a coupling constant which will freeze it, we will say there is some constant coupling, but I am changing R naught. If R naught is positive, so this function of phi, which is a number, phi is constant, so you can take a phi as a number. So, if R naught is positive and U naught is also positive, okay, this is always positive. If R naught is positive, then F naught is okay, you can set it to 0, but F naught is a constant. So, ignore F naught. So, this curve everything is positive. So, phi squared plus phi 4 looks like this. For small phi, which term will dominate? phi square will dominate, it's small. So, this should be quadratic, and large phi 4 will dominate, okay, phi 4. Now, what if I change sign of R naught? So, you will get a at near phi equal to 0, I will get a inverted parabola, right, because this term will be changing sign. So, for negative R naught I will get inverted, and for large phi of course I get positive because phi 4 is positive, u naught phi 4. So, it goes like that, okay. So, it goes like that. Well, I mean, so this is there and it is like this. For large phi they should be going together, no, because phi 4 is not changing, and this symmetric curves are not very good. Is symmetric both left and right, okay, correct. I mean, now we can find these positions, this position. How do we find these positions? Take the derivative, no, these are minima. So, I take the derivative. So, del f is 0, del f del phi is 0. So, that gives us R, okay, I think I have it typed, okay, R phi plus 1/6. So, that is this 24 factorial 4 and 4 multiply you get 1/6, okay. Some people just keep 4, but I am following a book, that book I said Kopitz, and that I am just following his book. So, 1/6, and so phi is a constant, please remember. At a given temperature I am having a some phi, okay, and of course, it will go to the minima. We know the free energy minima is what is chosen at a given temperature. So, the solution will be either this or these, one of the two. There will be unique solution at a given temperature. Now, what are the solutions for this cubic equation? One is phi equal to 0, in fact, this is pretty simple theory, and other is this. Now, this solution is valid only when R is negative or temperature is less than Tc, T minus Tc, that is why you are choosing R as T minus Tc, T is less than Tc. So, when temperature is below the critical temperature, then I will get two solutions, and these are the two solutions. So, what is this? This is positive spin and this is a negative spin. So, overall magnetization is either up or down, and both of them have same magnitude because of up down symmetry. So, these are the solutions. When so the Landau says, well, for T greater than Tc we will get a 0 solution, which is this is paramagnetic, or we get one of the solutions, negative or positive, this is a ferromagnetic solution, okay, and that is it. Now, how does the, well, of course, this is how does this point vary with m, vary with temperature. So, let us look at that one. So, you see phi goes as, I think I have it here. So, phi is the magnetization, is a phi is the number. So, it goes as square root T minus Tc. I put a mod, the minus sign, so it will be Tc minus T. Well, I will take a mod of this, okay. So, and it is square root. So, this beta is half, okay. So, how does it, if I make a plot? So, this is a temperature and magnetization, then it is 0 for T greater than Tc, and then this part is like that, okay. That is what I was trying to plot, and this is parabola, which is inverted parabola, square root T. So, this is Landau's theory of phase transition in a simple way, okay. But it turns out, I mean, I hope this is clear. This assumes the fluctuations are 0 and we get a mean value which explains this stuff. So, second order transitions are explained nicely by, well, not explained, this is a one model,